guess we can get started. So it's my pleasure to introduce Valentin Walther, and he's going to tell us about excitons that be like river patch. So thank you.
So yeah, thanks for being here so late and after dinner. I somehow feel reminded of the chameleon that we were talking about yesterday that has to digest. And so in the digestion process, actually, like I will be very slow. Like I will write everything on this computer here. And I really encourage everyone to just ask questions as we go along. And so the goal of this lecture will be to shift gears slightly, going away from atoms and molecules to the solid state, and in this case, semiconductors. And so my goal is really to like kind of show you where the similarities are and like kind of to develop the basic theory to basic simple theory of how we can describe semiconductor excitons. And in particular, I will be, of course, talking about Rydberg excitons here. All right, so this being said, I guess like the first thing to think about is how, or like that we know from atomic physics is that light interacts with atoms, and we're used to a situation where you have, for example, a ground state and you have some excited state. Oh yeah, I can use the microphone. Yeah. Okay, great. All right. So some photon would come in and excite this atom, right? And so the first question is like, how would such a process even look like? Like, how do we understand a similar process in semiconductors? And so in semiconductors, you would find yourself confronted with a situation such as this one, where in K-space there are bands. So for example, there could be a band that looks like this, and another band that kind of comes down from here. Okay, no, that's not me. So yeah, and so here's a, like in a semiconductor, there would be a Fermi level somewhere between the conduction band and the valence band. So let me just label those. So this is the valence band. And this is the conduction band. And the question is like, how can light induce transitions between these bands? And so to understand that process, we often, or like one can often use a simple Hamiltonian of quasi-free electrons where that are just described by kinetic energy that we know of free electrons and some periodic potential V naught of R. And so we all know probably from our like basic intro classes into solid state physics that the solutions of this Hamiltonians are Bloch wave, or the eigenstates of this Hamiltonian are Bloch states. So we can always write a state as a product of the so-called Bloch function and an exponential term. And so these are Bloch states. And so here, this K is the reciprocal, or the crystal momentum. This is the crystal momentum. And this lambda is the band index. So this could, for example, be the valence or the conduction band in this two-band model that I showed you here. All right, so oftentimes we describe excitons near special points of the Brillouin zone. So in this case, for example, near the gamma point, so the center of the Brillouin zone. And there's a nice way of understanding states around certain points of high symmetry approximately. And so this is what I want to show you just very briefly here, because it will lead us to a better understanding of light absorption between bands. So, okay, so here's the Schrödinger equation, the time-independent one. We know that each of these Bloch states is an eigenstate with an energy given by lambda and k. And now we can basically just insert the Bloch functions that we know are the solutions and try to derive a differential equation for u, for this periodic function u. And so when you do this and you just insert into the equation, you find that, of course, the momentum operator can act on the periodic or on the exponential part. So that just gives you a kinetic energy term. And then it can, of course, also act. So now what we're doing is we're inserting this psi into this function here. So it can break up and act on both the exponential and the function u, in which case you get two terms. So that's why there's no factor of 2 in the denominator. And then just the remaining terms that act on the function lambda k of r, and that is equal . Okay, so this ansatz is exact, but it's the starting point of perturbation theory typically, and the perturbation theory derives its name from this term, and because that's, I mean, the nabla here is the momentum operator, so that theory is called K dot P theory, and we see that like we can that for k equals 0, this is okay. So here this is K dot P theory. And so assuming that we know, for example, the solution at one point of high symmetry, so let's say like at k equals 0, we know the solution, then this ansatz allows us to do a perturbative expansion around that point, and get an approximate solution in the vicinity. So you first start at k equals 0, in which case the first terms just drop. Maybe I don't have to write this down explicitly. And so on. So the first terms are just gone. And then you can use these solutions to form approximate solutions. So if I just do second order perturbation theory on these terms, then we find that the Bloch function u of k in a vicinity around k equals 0 can be written as lambda k equals 0 of r plus, so like the sum now is over all the, I mean, like if we for example want to solve for states in the valence band, then the sum is in second order perturbation theory over the conduction band and vice versa. So the unequal index here so the unperturbed matrix elements, and here is the name-giving term k dot p, and of course that is divided by the energy difference. Okay, sure. P is the just the momentum operator. Yeah.
I was wondering, this K dot P term is like the vector potential. Can it be gauged away? P, charge party one.
Yes. I don't. I don't see how that would be possible immediately, but maybe. And for a Schrodinger equation, I mean, you would typically start with a time-dependent term to gauge it away. I mean, maybe that's something we can discuss later. I don't know off the top of my head if that's possible. And if you can get rid of that term, that kind of like that would solve the problem exactly. So maybe not, but and similarly, you can write the energies in terms of the unperturbed energies plus, of course, the kinetic energy term. And here you find that there's a second order contribution. Oops. Like this. Here, 0. All right, and so, sorry for the mess here. So the second term actually is kind of interesting, as you can absorb that term that's quadratic in K. You can absorb that into this first term here, and that will then make, like, if you combine these two terms, that is a first description of an effective mass, where the electron mass m0 becomes renormalized because of the crystal potential. Okay, but so with that introduction, let's get to the point that I raised, or the question that I raised in the beginning, and that was optical transitions. So the light matter interaction, and I guess we've seen that already a couple of times. The Hamiltonian is simply the dipole Hamiltonian. So the E field times the electronic operator R, but it's at this point not immediately clear how you would take matrix elements off this state. So let me show you how to do that. So basically, to now look at the transition matrix element between an electron in the valence band to an electron in the conduction band, we would have to evaluate a matrix element of this form. So lambda k, that's one Bloch state in one band. We take matrix elements with this light matter, so LM, light matter Hamiltonian, with some other Bloch state. And so, of course, then inserting that, to get that this is lambda k, R lambda k prime. And so to see the structure of this term, let me show you a trick. So the trick is that that if you want that you can evaluate this matrix element here by first looking at the commutator between R and H, the expectation, or the matrix element. So okay, so one thing, we want to look at interband transition. So here this is lambda not equals lambda prime. We'll use that later. But so if we want to evaluate this term here, so that's kind of a side comment here, or like a trick. And if you expand this matrix or the commutator, you know that the Bloch waves are already eigenstates of the Hamiltonian. So this is nothing but psi lambda k with the matrix element of R k prime times k prime minus h bar lambda k. So that's part of the story. The other thing is that we know what the commutator, because we know the Hamiltonian, that was just the one that I gave you up here. This Hamiltonian, so the commutator between R and H can directly be evaluated. And this is IHP over M0, just from the commutator of the momentum operator and the position operator. So with that, we know now that the matrix element that we're seeking, this matrix element with respect to R, can conveniently be written in terms of a matrix element. So I canceled here factors of h bar from the numerator. Okay, so we express now the matrix element of this operator R in terms of a matrix element in terms of P, momentum operator. And so what remains now is to evaluate this matrix element of P. So we evaluate, and this is the last step in this part. So we want psi lambda k P psi lambda prime k prime. And of course, we can, for example, choose a position representation here and just evaluate the integral. Here's the momentum operator. All right, so now we know what the Bloch wave is. Again, like that's this exponential times the Bloch function. And we also know that momentum operator is, of course, the derivative. So we can evaluate this and end up with an integral. So we can write this in terms of minus I k r. So that comes from the first function here. All right. So basically, I just and sorry, I missed. All right. So here I just applied the momentum operator on this e to the IKR. So the next step is to say that we know from this perturbation theory, from this KP theory, we know that this U function can be approximated quite well, actually, across points of highest symmetry by the value at a given position or at a given K. So that I summarized these terms here. So it's okay, so now like what can be done, of course, in semiconductors is because they have a periodic structure. So an integral that goes over all of space can be decomposed into many integrals over each individual, or like each individual crystal cell in this case. So we introduce a new variable. So R can be written as Rn. So for a given crystal cell plus the, I don't know, relative coordinate here, R prime. And so what we end up with is an integral over this new coordinate here, and a sum over all the matrix, all the crystal cells. All right, but now we can perform the sum over the capital R's. And so that just gives us a delta. So that's a delta K prime. So the momenta have to be the same times an integral. And so in this integral, we see that there are two terms. So one is the integral over just a number, h bar k, and the other one is the matrix element with respect to that operator, p. So because in the beginning we assumed that we're considering transitions between two bands, the lambda is unequal to lambda prime, and so the first term cancels because that's an orthogonal state, and we're left with just a matrix element of the second term. This is actually 0 R momentum operator. Okay. All right. So that completes this actually. Let me just summarize. So now we know, like putting all the terms together, we know that the matrix element between two states, between two Bloch states, with this light matter Hamiltonian, so going from one lambda to another lambda, can be written as minus E I over M0 just need to scroll up a little to get this onto the page. Okay, so what does this mean? So we see an expression here, and of course it has, it's proportional to the electric field. It's also proportional to some integral that we now know how to evaluate. But what really is important is that there's this factor here, the delta K and K prime. So this shows us that transitions between states in the Brillouin zone that are induced by light are basically vertical. So they take you from one K to the same K, but across bands. So just write this. So light induces vertical transitions. And from this term here, we also see from the P term, we see that the parity of the bands between which we want to transition has to be opposite. Okay, so that's an important result, and that's very different from atoms. So now, like, we understand these transitions. We understand these transitions as just going vertically in K-space. And I guess like an intuition for this can be gained from seeing that the photon momentum, like of an optical photon, is very small compared to the energy that or like kind of the crystal momentum that an electron would have. So basically, the wavelength of light is much longer in real space than the crystal size that defines the size of the Brillouin zone. So that's like kind of the intuition behind this. So the photon doesn't have enough momentum to really kick the electron much around. Okay, are there any questions about this? Yes.
How do you know that the denominator is not zero?
Because we assumed that the bands are separate, or like that there are different bands. So you would. That's an excellent question, actually. Okay, so if we go back here, so what we have are transitions from one K point to another, and we assumed that we consider different bands. Of course, this theory will break down if the bands touch. But all the situations that we are considering are for separate, for bands with a large separation. You'll see why in the next section, actually, because otherwise exciton states cannot exist. Yeah.
Your map looks very reminiscent of the isolated forest.
Yes.
You're saying 1 degree of freedom projecting. In this case, so I wondered if there was, or surely or something, there were different phase shifts. The two bands, you might have shape of satellites like isolated core.
Yeah, I don't know the answer to that question. I know that there are like sometimes there are barrier effects, like when there are certain, like that can maybe relate to this question. So if you have certain structures of the like non-trivial topologies, for example, of the bands, then you can get interesting physics. But I like for now we'll just like consider this very simple case where we have trivial bands, and they will even be parabolic. Yeah. Okay, so the next thing that I would like to discuss are, of course, excitons. So how do they now enter the game? And so let me just describe what the observation is that one typically makes. So let's take the simple bands that I already mentioned. So we have two bands. So some energy 0 here. And so we measure some absorption spectrum. So now you start illuminating that system with light. And so here I plot the energy as the y-axis and the absorption as the x-axis. And so when you come in with some light, then you see that at a certain energy, when the photon energy is just sufficient to make transition, or like to induce transitions between the two bands. So this would be at this energy. Then you get absorption. And so in 3D, the absorption grows, or the absorption grows with the density of states. And in 3D, this density grows as the square root. Okay, so one thing that's maybe important. So this difference between the conduction and the valence band, that's the energy. This energy is called the band gap, Eg. And so you get this type of behavior. And actually, just for your information, so if you it's maybe kind of curious. So and maybe you remember this from solid state physics. Also in 2D, the density of states is different. It's actually constant, so you get something like this. And in 1D, the density drops off like 1 over the square root. So you get 3 different types of absorption profiles here. So this is like 1D, this 2D, and this is 3D. So anyways, I mean, I will consider the case of 3D for now and 2D a bit later. But what now happens is that instead of just seeing this absorption, what one sees in experiment is that there are also some peaks here that appear below the band gap. So you could maybe you get a couple of lines here. And so these lines are excitonic lines. And a lot of what I will be talking about will be about understanding these lines that appear, although the energy of the photon that you send in isn't quite enough to transport an electron from the valence to the conduction band. So, I mean, I guess in this, let me just again draw this band model. Oh, sorry. So this could be our bands. And so what happens really in a semiconductor is that really like this valence band is all filled with electrons. And so when a photon comes in and promotes one of those electrons from the valence to the conduction band, then we can of course describe this many-body electronic system with an electron here and a hole in the valence band. But it is actually much more efficient to describe this system not like this, but by going to just like this particle hole picture that I guess Peter already described yesterday, where instead of describing all the electrons, we just describe the hole. So we just have an effective description where there's a hole here and an electron here. So in that system, we can completely forget about all the other the electrons, and we just have this this pair of an electron and a hole. So that could be a free transition between these bands. And note that, of course, again, like this transition is vertical in K. And okay, so now it is very nice that we can describe this entire system by a Hamiltonian that I will just sketch. So because we will use it a couple of times, so I can now formulate an effective model for this electron in this electron hole language. So again, in K space, we have a kinetic energy for the electrons. And so now I use just second quantization to write this. So there's a kinetic energy term for the electrons. And at the same time, there's a kinetic energy term for the holes, of course. So the H of K's are the hole operator at a given momentum. The C of K's are the electron operators at the corresponding momentum. And then, of course, there's an interaction between electrons and between holes and between electrons and holes. And so in momentum space, I just described this by a standard scattering term here. So that's the whole interaction. Then we have a corresponding term for the electron-electron interaction. We'll not write this out fully because we will, as you will see, that term is not so important. The most important term is the electron-hole interaction. So it has the same shape, form, functional form. So that's the electron-hole, and so that the electron-hole interaction, and that could actually be, it's typically Coulomb interaction, of course, between charges, a positive and a negative charge, but it can also be screened in some certain geometries. In 2D, for example, that could be a modified modified Coulomb potential. All right, so that's the Hamiltonian. And so now I think the easiest way of understanding excitons is actually by realizing that we try to find states that are excited by a single photon. So they are created at the same momentum. So you always, like, you produce holes and electrons at some k, but a certain combination of them. So a wave function that describes this is fairly simple. So let me just give you the simplest, whoops, sorry. Wave function here. So this a state, an exciton state could, for example, be some envelope in k space, alpha of k, and now it consists of many pairs of electrons and holes at their momentum. So why did I write a minus here? So that's basically convention. If you look into textbooks, you'll find many like different conventions, but I like the idea that if you rip out an electron from the valence band, then the hole has the opposite momentum because it's a vacancy basically. And so here, like, the overall momentum of that excitonic state would be 0. In fact, the more general an exciton can, of course, also have a momentum. And so if it has a momentum, then the same idea applies, except that there now also is this momentum index. So this is HKP, the center of mass momentum, basically. And so now you can see overall this state has momentum P. So if you add the two momenta up of the electron and the hole, you will find the state has momentum, overall momentum P. And so, like, how do we now find excitonic states? And so the easiest way, in my opinion, is to use a variational ansatz, which is this one. So that is a general state. And now we just formulate a Lagrange function and minimize basically the Hamiltonian. So we minimize the Hamiltonian, the electronic Hamiltonian, with respect to that ansatz, with respect to the excitonic wave function, making sure that the state is normalized. So this is given by this last condition here. And so, of course, this calculation is a bit tedious. Now you have to basically take this ansatz here, this psi, and the electronic Hamiltonian, or the Hamiltonian, and evaluate all the matrix elements so that you end up with just with an equation for the alphas. And so instead of going through this, I will just give you one example. And if you want, you can try it yourself on some other terms, and ask me later if there are any questions. Let me just show how it works for the kinetic energy term, for example, for the electrons. So that term from the Hamiltonian would be Tk, like just the C dagger K C K. And I'll take an expectation values with this psi here, and we do the general case where there's also a P. Okay, so to start with such a calculation, you just have to insert now the excitonic wave function. So 1k for each of the excitons. And so now you get a vacuum expectation value. So the 0 is like no exciton or no excitation whatsoever. First term, Tk energy Tk Ck, and the second term, so C All right, and now we basically, like the way to do this is to commute the operators. Those are fermionic operators, so you just switch them around until the annihilators hit the right side, or the creation operators the left side. And when you do this, you find that all these terms, all the sums collapse, except for one. And so that last sum is just diagonal and contains the electron. The electronic kinetic energy. And so actually, like when you do this for all the terms, so for the kinetic energy of the electron, for the kinetic energy of the holes, and then the only term that contributes is actually the interaction between electrons and holes, then you end up with a closed form for the Lagrange function, which looks like this. So you have the kinetic energy of the electrons. This is the one that we just calculated here. So I switched variables to go back. I renamed K prime K. So that's the first term. The second term comes from the interaction between electron and hole. And this term is not diagonal anymore. And then there's just the normalization term. All right. So that was the technical part. Now, of course, if you want to minimize such a problem, then you now do the variation with respect to so now we want an equation for alpha. So you vary this Lagrange function with respect to the alphas. So now taking the variation to be 0, we get an equation of motion, or yeah, we get a closed equation for the alphas. And so when we see this, and now, for example, we could assume simple bands and now simplify this tremendously by, for example, looking at this expression. And if these are bands or quadratic bands with a whole dispersion, like with a whole mass m whole and an electron mass m electron, then this entire thing is nothing but h bar me. So that would be the term from the electron kinetic energy. So this gap comes from this first term. And so you can actually very nicely summarize these energies as the gap energy. So like, because the electron energy is the kinetic energy plus the gap energy plus a relative momentum, or the kinetic energy of the relative momentum plus the center of mass. So here I define mu as we have seen already before. So that's the me times mh plus m, and the total mass, of course, me plus mh. So maybe that's already familiar to some of you in K-space. So you have a kinetic energy term that's diagonal. You have some term that's non-diagonal with the interaction. But actually it becomes much more familiar the most probably if we transform this into real space. So the real space representation of that equation becomes, now we get the term that is the derivative with respect to the center of mass minus a kinetic energy term for the relative momentum, so small r, with a reduced mass plus this is the potential EH. And so here I subtracted the gap energy, alpha r. Okay, and this equation, of course, is pretty familiar. That's just an equation for a two-particle system. With this is the Coulomb energy, then that's the hydrogen equation, basically, that is in motion. So like with the center of mass. So of course, the first step to do is to separate the center of mass. So we can write this total wave function of the exciton that consists of a relative motion and the center of mass motion. We just isolate the center of mass motion. So here this is a capital K. I don't know, this is probably not so nice. Let me try to write this a little nicer. Capital K times R. And so now that, of course, removes all dependence of these capital R terms. And we get a nice closed equation just for the relative coordinate. So that's the total energy minus the gap energy minus the center of mass energy. And so in the I mean, this equation is in semiconductor physics, it's often called the Wannier equation. Which basically looks like a hydrogen equation or Schrödinger equation. And hence the name also, like these excitons are called Wannier excitons. So another comment, this energy here, so this is the binding energy of the exciton. So we call that E nu for the nu state of the exciton. So okay, so let me just, because there sometimes is confusion, like in the field, like whether an exciton is a localized particle or it's a delocalized particle. So let me just clarify this. An exciton is a delocalized particle. But now, oops. Now note that this is the center of mass momentum. So in this picture, one could basically say that this would be the band gap, and now we can have excitonic states that lie below the band gaps. So those are, so for example, this state or this state, and we give them a label nu, and each of these states is now not a single particle state, but this is basically an electron hole pair that is bound together by some interaction. And this energy here, so the energy that separates the excitonic state from the band gap. So, here, this energy E nu, this is the binding energy of the Rydberg, of the excitonic state. And so you see that, of course, and this, because this equation here, this Wannier equation, permits many solutions that we label by E nu. In some semiconductors, there's a Rydberg space. So just very much like in atoms, there can be multiple solutions to that we call the Rydberg series. So just let me write this down. So these Wannier excitons. So I don't have to explain. There's another type of excitons called Frankel excitons. If anyone's interested in that, I'm happy to explain that later. Unfortunately, I don't have time to do that now. So those Wannier excitons are bound electron hole states with a free center of mass motion. And with a series of excited, so Rydberg states. Okay. So this brings me to the point where I think I've introduced what excitons are, what band transitions are, where they come from. Are there any questions as of now before I go on? Why are they equal? Because this is, okay, excellent, thanks for asking that. So the overall wave function of an exciton is given by this. So it has a plane wave in the center of mass. So basically, that's why I call it free. So the center of mass of this electron hole pair can be anywhere in the crystal, but when I have the electron here, then then the hole is right next to it, and that's in the bound state. Yes, exactly. It's localized. It's the bound state in the relative coordinate, and the free state in the center of mass. Yes. So yeah, okay. So let's in an experiment where there would be, for example, one photon in a wide beam that enters into the semiconductor. Then you would have an equal superposition of having the exciton in any one of those places with a relative coordinate like in a bound state. So this is very much alike to the W state actually that Tillman was talking about today, I don't know, where you just kind of have to have a superposition of having the excitation here and there and everywhere else. Yeah. Okay, so maybe I can start with the first. Oh yeah. Yep. Mm-hmm. No, then you have to also change the internal structure of the electron of the exciton. So then you will not excite an S state, but you will excite a P state. So overall, the momentum, like the transition operator is of odd parity. So it can only connect states of opposite parity, and the overall parity has to be there. So if the bands have the same parity, then you cannot have an even parity state. So that would then be a P state. As in the case of cuprous oxide, I will come to that actually just now, but only as a, okay, so the next topic that I will talk about, and I will just take the first point, the first part of this, and then we can relegate the rest for Thursday. So properties of Rydberg excitons. And so the point I wanted, like the first topic there is the exciton oscillator strength. So kind of like now we talked about all of this, like this, the band-to-band transitions, and we talked about what an exciton is, but now what is the dipole matrix element basically that I have for creating the exciton somewhere? I think that connects nicely to the discussion that we had. So that's why I would, if you give me 5 minutes, discuss that now. So we know this light matter Hamiltonian, and we discussed it in detail how it induces vertical transitions in the bands. So I can also I can now translate this Hamiltonian second quantization into this electron hole picture. So now in all momenta in the Brillouin zone, it will induce transitions. So here I now make for definiteness, this is the conduction band, H light matter, the valence band at the same K. So that's I will shorthand for that light matter CK VK. And now this Hamiltonian, or this optical, this light matter interaction will basically create electron hole pairs. Yes. Which left index? Okay, so yeah, this is a C for conduction. And this is a V for valence. Yeah, thanks for pointing that out. So now we can just calculate matrix elements again, and you will see that a lot of these calculations have the same shape. So we calculated this with the for like the Lagrange function, calculating these matrix elements, and here it's the same thing. So we're asking, like, what's the overlap between the vacuum state, so nothing, and an excitonic state? So this is, oh sorry, this is not A0, this is A mu. So this could be any of the Rydberg states that we discussed. So any, so what's the matrix element here? And so let me just give you the first and the last step. So of course there's a matrix element HLM. So with the conduction band at K, valence band at K. Plus the Hermitian conjugate, 0. And so when you go through this calculation, you find at the end, okay, so that's actually, that this is HLM so it's the matrix element at K equals 0. So, and then it has a sum over all of the, a sum over K of the momentum space wave function of the exciton. So does someone like want to give a guess? Like if we sum over the K space wave function, so if you sum over a Fourier, or like if you sum over a Fourier transform, does anyone know what that gives? Yeah. Exactly. Exactly. So it's basically you could just insert an e to the I k r equals 0 here, and then that becomes basically the Fourier transform. And so in the end, we see that the transition from the transition matrix element for going from nothing to an excitonic state is basically given by the light matter like the light matter Hamiltonian at K equals 0 times the wave function alpha nu at R equals 0, so in real space, And so last comment from my side before we can take questions. So the oscillator strength is the square of that. So it's alpha nu H light matter 0. And that is approximately H light matter. So this is alpha nu here squared. So basically what we see here is that the probability of exciting an exciton is proportional to the square of the relative wave function at 0. So basically the probability of exciting is proportional to the probability of in any given excitonic state for the electron and the hole to be in the same place. maybe you can understand that from the reverse process. It's actually easier to understand that. So if they're in the reverse process, then they can decay into nothingness, but actually like, because it's a Hermitian process, so like the inverse, by sending in the photon, you can actually only excite the electron and the hole in the same place. So if you have a wave function that's very far, where the electron and the hole are very far apart, then its oscillator strength is going to be small. And so that is just like, from that we can see the scaling of the Rydberg series, Rydberg scaling. So if you evaluate hydrogenic wave function, for example, and take the square of the matrix, the square of the wave function, the relative wave function at 0, and you plot it as a function of m, then you will see that this alpha nu of r squared goes down as 1 over n to the 3 for so-called allowed transitions. So allowed transitions are transitions where the matrix element, the corresponding matrix element of HLM, is not 0. But this is not 0. And then there's this other case, which is relevant for a cuprous oxide, when that is the case. So when the transition matrix element at 0 is 0, then we're talking about a forbidden transition. And I will not derive this, but actually then the scaling is n squared minus 1 over n to the 5 for so-called forbidden transitions. Transitions. And that's exactly the case, for example, in cuprous oxide, which we will talk more about on Thursday as an important example. But if you want more info on this, there's actually a very nice paper from a very old paper by Elliott. Physical Review 108. And that's from 1957. All right. Okay, so I think I really gave you a rundown of what excitons are, how they're created optically, and what their optical oscillator strength is. So thanks for bearing with me and digesting dinner. If there are any questions, please just shoot. Thanks. I mean, okay, so I decided to turn this around and start with the formalism. And this is what we'll do some more formalism on Thursday, and then I will like show you like what research has done in the last couple of years. So actually, like excitonic states are very old, so they have a history of like 70 years or so. But that highly excited Rydberg states have been observed is a new development of the last. I mean, we heard it like from 8 years or so. And so, I mean, you will see that there are lots of different research directions on the fundamental physics of these states. And I guess it's like at this stage, anyone's take like on why these states are interesting. My personal opinion is that these Rydberg states are a way of inducing interactions, strong interactions that you would otherwise not get in excitonic systems. So this could be, for example, interesting to these excitons have very interesting polariton properties that I will also talk about on Thursday. And so one can think about like producing strong correlations and going into this direction that Tillman also talked about of making photons interact in a semiconductor. So that would be one direction. Another direction would be using these states, for example, for sensing many-body states. I mean, we can talk about this. This is actually something that I will not mention on Thursday. Oh, yeah, that's an excellent comment. Sorry, I should have mentioned this. So, so mu, like this is like a collective index for all like for a collective quantum number. So this would be n, m, l, like whatever quantum numbers you have. If there's a spin quantum, if there's spin 2, then maybe a spin quantum number. And here, what I mean specifically, this n is the principal quantum number, as you would know it from other Rydberg states. Yeah, sorry, this has become so ingrained, calling n the principal quantum number. Yeah.
So in the
Mm-hmm. So yeah, excellent question. So V of, like, this is the electron hole interaction. So as a starting point, this would be a Coulomb interaction, and hence you get a hydrogen-like spectrum and very much like the Rydberg series that you're used to. That said, there are lots of modifications of this V of E of R that could, for example, come from screening, where the tails of the Coulomb potential are no longer of this 1/r type, but for example, get an exponential tail, in which case the infinite series of Rydberg states that you're used to from atomic physics or from hydrogen gets truncated, and you just have a finite number of Rydberg states. Another example would be two-dimensional materials, where the electron-hole interaction is screened in the plane, but not outside the plane. And there, actually, this V of R becomes the sum of the Struve and the Bessel function. So there, you kind of get the opposite limit, where the long-range tail is 1/r still, but the short-range tail is not 1/r, but has a logarithmic decay. It's actually kind of nice. That can be shown analytically. And then you get like modified series. So you get like modified spectra. You get, no degeneracy in certain quantum numbers that you would be used to in hydrogen, for example.
I guess I have one question related to what Tellen said, but I don't know if this is well. What did you mean by forbidden transition there? Is it just a quadrupole, or is there something else?
So
is there like a perturbative field?
Yeah, okay, sorry, I should have mentioned this a bit clearer. So what I like, forbidden transition is defined. So you always have this matrix element.
So it's still a dipole transition.
It's a dipole transition, right? So kind of, okay. So let me just illustrate this. So if you have any transition to an excitonic state, then basically the transitions, or like the matrix element, is dominated by, because the exciton is kind of large. So it's like it's this k equals 0 transition at a given at k equals 0. This optical matrix element for going from the conduction to the valence, from the valence to the conduction band, and that has a value. But in some semiconductors, because of symmetries, exactly at k equals 0, that matrix element is 0. And so then it actually becomes relevant that the wave function, so although the exciton is large, so in k space it's small, so you kind of get a wave function that maybe looks like this in k. So then, because the center is 0, then you have to take derivatives and take because off the center, then it's not 0. And so it's these terms then that allow an optical transition away from k equals 0. And that's what you call a forbidden transition. Mm-hmm.
And does this reverse scaling depend on
Yep, that's a good question. It depends on some properties of the potential. So I think like if you want this, so if you want the scaling at large principal quantum number, then probably then your tail has to be one of R type at large distances. So then probably you can live with the logarithmic decay or something else at short distances. But actually, I mean, I have the notes for this for tomorrow, like kind of on how to see the asymptotic forms of these functions, but probably on Thursday. But I don't think, or maybe we can discuss it separately because time is, I think, a little short. But yeah, I mean, like this is the Rydberg scaling that you would be used to in atoms, and also there, like right, like. Exactly. So I know, like this is from a hydrogen model, and to one over n to the 3 is what you would get just from hydrogen. Yeah.
Every time you excite a certain area in your circuit, you have a fully delocalized excitation.
Mm-hmm.
If you have one photon, you set this W state, you don't know which lattice side really carries the excitation. If you have two photons or more, then I have a little bit harder time just to imagine how this actually looks.
Mm-hmm.
In a gas, I sort of imagine at least there are 3 atoms, yes, they are in the ground state, and now I'm exciting them to the lattice state. But here you start from a vacuum, totally empty, and you are creating those exit points.
Mm-hmm.
And so that must be sort of a different feature, different
right.
thing. I mean, any experiment that is going to happen later on is not perfectly important. There's also an experiment have a huge number of photons.
That's right. So it's kind of like, I think like it maps to the atomic case when you have much fewer photons than atoms, in which case saturation doesn't play a role. So then you can imagine just like I create one atomic excitation here, one atomic excitation here, and they don't really influence each other. And that's kind of the same here. So oftentimes one would describe these excitons as bosons, as composite bosons. So you kind of like you neglect the saturation effects. But actually, like there have been experiments also like at high intensities when saturation does play a role. So basically what happens then in these situations is that for atoms, you would just somehow think that like once an atom is excited, right, I can't excite it again, the same atom. Here with semiconductors, the same picture would be like you excite, like you already have a certain fraction of the K-space filled. And so then like kind of by Pauli exclusion, you cannot excite the same states again. And so that actually maps very nicely onto the local blockade. But in everything that I will be talking about, I'm considering this low excitation limit where the number of excitations is much smaller, or like the density times the volume of an exciton is much smaller than 1. So like I can restrict to this bosonic limit and neglect saturation effects. Yeah. Right. Yeah, like kind of the question with the phases, right? Like, will the phases, yeah, I mean, it will, of course, dephase pretty fast. Like the dephasing times of excitons are short. So like while you excite this W state, then pretty quickly, probably like the state will become a different, will dephase. Mm-hmm. At least for the excitation, my picture is that it's completely delocalized for like in your beam. Then probably the phasing effects act on that. Yeah.
Let's do the experiment. We take the crystal, we have a big beam.
Mm-hmm.
We have this delocalized excitation. Then we switch off the laser and we wait. Then there's some dephasing, and then we're going to look at the fluorescence of the decaying exciton.
Right.
Do you see this fluorescence? It has to come from somewhere. So you see this as a localized spot somewhere.
Yeah, this would be kind of like, is it radiating into 4 pi or is it like kind of?
Yeah, exactly. So it's decay radiating like 4 pi, is that localized? Or is it radiating in the forward direction?
Mm-hmm. The answer is probably there's a non-radiative decay channel.
No, that's all.
But okay, so just for
difference in the radiating either decay back, preserving all phases, and then it will if the photon is the photon in the direction where it came from, or it will direct the wave and distribution, which you can with the microscope, yeah, localize it.
right. Yeah, I don't think the experiment has been done. Yeah.
Can you treat the interaction between the excitons as like dipole-dipole interactions, or do you have to take into account correlation?
Well, okay, so this is something that I will be talking about. So if you have like these Rydberg states, like let's say in the ideal limit, I just have 2 Rydberg excitations at a very low density and then large interactions, then you just have the dipole-dipole interactions and no correlations from the fermionic character of the exciton. If on the other hand, you have ground state excitons, so very small excitons, then their dominant interaction is by exchange. So really like collisions and the Pauli principle that makes between the electrons poles that make them up.
So if you talk about what is the process? The object, I mean, it's not the, I mean, in a vapor, you could say it's the motion.
Right.
But I mean, they are not moving.
Well, I mean, they're moving a bit, right? Like just from the photon recoil, just slightly, but that's a collective one, all in the same direction. But I guess, so phonon interactions would be probably most relevant. That depends on the material you're looking at. Yeah, on the phonon channels. So interactions with acoustic phonons, basically. There's also, there all can be plasma effects, but if you are in a perfect crystal, there's no plasma. Perfect crystal, 0 temperature, then you could just still emit phonons. That would be the only dephasing channel. Electron-electron interactions? Yes, but they're kind of like, they're accounted for in this formalism. So this is like kind of the electron-electron interaction is basically an electron-hole interaction, right? There is no hole. So that kind of is the one force that binds the exciton, and then you have the remaining forces are the ones that would be described by the dipole. Okay, so for now, this is just like single part. All of this is single particle physics. Oh, you can get interactions between two. Well, I mean, that's an interaction, right? I wouldn't call that dephasing.
But I'm still struggling sometimes with this system. Because if I compare it now to the atomic case that I was discussing this morning, we have a density of atoms in the first place, and you have another density of excitations, if you like. So let's say you send a single photon into a dense medium, then you see this dipole-dipole interaction. Although you have only a single excitation.
That's right. I mean, like this is something that I also wanted to ask you.
And in your case, I'm not so sure. Is this
no
Lorentz shift or this dipole-dipole shift actually there?
No, it's there, but it's already included because you never have like the reason you have it for atoms is right that you compare an isolated atom with an atom in the surrounding range. Like an exciton never exists.
Okay, so this when you define the exciton binding energy or the position of that peak, it already includes that collective shift. And this collective shift is actually very large here because the distance between these little dipoles is just the lattice period. Right? That's the density that you would take here.
That's a good question. Yeah, my picture has always been that it's in there, but like when you look at the calculation, it is not.
It doesn't appear anywhere.
It doesn't appear like kind of like you anyway start with.
It should, for example, be geometry dependent. Yes. So, for example, if I have a thin slab versus a long tube, then,
like in your
this shift is blue or red or whatever. Yes. So, in your treatment, the geometry doesn't show up.
It doesn't show up yet.
So I'm confused. what is going on there? Because my picture in real space, and let's take type binding model. Yes. In every position, I have a harmonic oscillator. Yes. And I have the ground state, ground band, first inside the band, like this. So this has even parity, this is an odd parity, and so on. And these are the selection rules that we're discussing. I find it just all it down to harmonic oscillators. Yeah? Okay. This, and that is the lattice period, A, yes. So I can have an electron here, here, and so the density of my gas basically is just 1 over A cubed, yes. It's an extremely high density. Now I have an oscillator here, the dipole moment. I have an oscillator here with the dipole moment. And if I look at this collective state, at least in a gaseous sample, there's a shift that
it goes with the Green's, it's like it's the Green's function integrated over things. Yeah. So, I mean, I'm trying to. I don't have the full answer. Actually, like a similar problem with rabbits. We try to couple, like try to extract this like from first principles. If you have a sheet with this excitonic wave function, that you couple it to all like actually the quantum light modes, and then like this kind of model has to come out where you can, like the Lindberger geometry, like you integrate everything out, and then you should get this here. And I was just like assuming, I had this in mind, but you get this coupling, but then you can just like put it into, you can renormalize the energy of the sonic states. But you're right that if you just start from this model, like just take m, like the mass of the hole, the mass of the electron, this attraction, that's not there. So probably, I mean, like, I'm not sure if like how this A will show up.
Yeah, I'm not sure. It never shows up in this.
But it like even in the continuum model, it will just say okay, like I have a sheet I can excite anywhere. It's just continuous. I get integral. Let's say that diverge.
I mean, if you do it in the argument not by Steinberg paper, but by Lorentz himself, yes, like 100 years earlier. Okay. He just uses the Clausius-Musotti relation, yes, with just his Lorentz model, yes. And there he sees that there is a shift there, yes. Yeah. And so I'm wondering what would the Clausius-Musotti argument sort of do here, yes. Because that is sort of the unique field, easiest description of that.
Right, but it is kind of like quantum. It's a quantum. Like,
it has nothing to do with quantum. It's like just it's a Lorentz model, driven harmonic oscillator.
Okay. Yeah.
In a dense arrangement of oscillators here. Yes. Fully classical, and it's just harmonic oscillators everywhere. With a certain density. Then, if you apply Clausius-Musotti with a Lorentz model, yes. Where the width of the Lorentz is, of course, much smaller than the absolute frequency, but that's the case here. That's also the case for you. And you just get the shift. Yeah.
I'll have to look at this. Where this A comes in and like how to put it on.
Good. Yeah. It's very nice.
But
looking at this from first principle.
So like you're now like with these dense gases, I mean, like from your talk, it really looked like, I mean, why do we even ever need Rydbergs, right?
Yeah,
like it just make it.
That was asked because you need very high densities, yes, 10 to the 16 per centimeter, something like this. That's the last density, but it's probably impossible, yes.
But do you think? Okay.
Well, actually, there's a fundamental difference. Because, I mean, in the Rydberg location, the Rydberg location is not caused by this dipole, it's caused by this.
Yeah, exactly.
Next Rydberg level. So the frequency of the dipole is the terahertz, or at the Kepler frequency to the next one here. If I have a two-level pattern like this, then it's only one frequency here. Here I have two frequencies. That's the Rydberg phase, Rydberg blockade phase, and the other one is this Lorentz shift phase. Yeah. That's just G and E. That is G, E, and E prime. Yes, and the interaction comes from here. Yes. So this means that in the Rydberg blockade, if you just have a single excitation here, yeah, well, nothing happens. A single photon does not see a shifted.
Yep.
So it doesn't experience any shift. That's different here, yes. And that's exactly connecting to what's exactly connecting to. This is already shifted, even if I had just have a single photon, yes? Because it's from the very beginning, sort of a coupled system of oscillators. That's, yes.
Well, it's just, I mean, to me, I guess like if you have a high density, right? So then like the shift from the first to the second photon, and it can be that large. That's surprised me. So because you kind of like, if I think about these bands, as like I get
so the picture is that if you have one atom here and the other one here, how do they interact? They exchange a virtual photon. If there are many other photons from outside, yes, then these atoms are driven by those photons also. Yes. And the difference by this one virtual photon in their dynamics doesn't play a role anymore. if you start to saturate those dipole moments here, of course that is not captured by the Lorentz model anymore. Saturation effect. No longer just a harmonic oscillator. It saturates. Yes. At that point, that shift goes away because these dipoles are driven so strongly by the external field that the perturbation by the one photon that is virtually exchanged. That's why the measurement and the theory shows you there is a shift at the gamma that is finite, in our case blue, and it goes to 0. Yes, and it goes there in a quadratic fashion. Yes, and now, yeah, if this is one photon and this is 2 photons, then the shift depends on the number of photons. Yes. And now, of course, you have to make sure that that saturation happens already for 2 photons, let's say. Yes, yeah, or 3. Yes. That's the point. Yeah. So that's right. I mean, like I kind of think about it like more like in this, like kind of the spin model picture. So if you have like large densities in atoms, and I mean, if you want to analyze this for the first excitation, then you get your shift at first. And so now I could diagonalize it for 2 excitations, and I would get the second shift. But now, like because I have so many levels, I'm kind of surprised that you kind of like with the idea of getting photon bouquet, that you would somehow, I mean, like in the Whitworth bouquet, you really shift like all the states out of resonance. But here, you have so many states that all shift. And then if I compare should I compare the 2 excitation manifold? Like I take this entire spin model, I diagonalize it for 2 excitations, and I diagonalize it for 1 excitation, and then kind of see. Yes. I would have to open up a gap basically, so that my photon. That is what's happening. Well, this is, if you have 2 excitations, then you have the super and the subradiant modes. Yes. And then if you have more and more, then basically that's how I view this. Yes. Then there are states that are more symmetric, let's say, and they are the superradiant states, and other ones are the antisymmetric. Exactly. Radiant states. And there's a gap between them. Right. Yeah. And then, okay. Yeah. So yeah, but this initial shift here, yes, this is just the Lorentz model, already there for a single excitation. Yeah. Sure. Yeah. And it becomes more complicated if you have more excitations in there. Yes. Exactly. Because then you get more states and so on, as you say. Yes. And then, but I kind of like so if you have lots and lots and lots of states, like lots and lots of atoms, then probably like the shift for the second photon is almost like twice the shift for the first. Yeah, it goes quadratic here. Yes, so it's not going. I mean, what you say is would go linearly down. Yes. Yeah, but it's like a quadratic behavior here first. Density. Yeah. So this S, what is that? That is the shift of the line. Of the line, yes. That's. I mean, my plot is a little bit confusing because I'm having a logarithmic scale here. Yes. So in my plot, it looked like this. Yes. But you have to be. I mean, this is a logarithmic scale here. If you plot it in a linear scale, it just looks quadratic. Yes. It just comes down. But then you can still, for that quadratic behavior, you can define the chi3. Yes. Sure. No, I mean, I'm kind of surprised it's quadratic. Because if you, I mean, quadratic is something that you would get for an interaction, right? That is an interaction. It is an interaction, but you also have the single particle effect. So if I now, I'm just wondering, like, if you have many atoms and just 2 photons,
then the interaction should be kind of small compared to the limit. I mean, like then kind of, I would expect that every photon kind of produces the same shift.
No, there is a shift even if there's no photon. I mean, even if there's only a single one. Yes,
exactly.
So it's a coupled. I mean, the way I look at it is it's just a lot of harmonic oscillators that are all coupled together. Yes, again, harmonically sort of coupled together. Yes? Because this virtual exchange here is just another coupling between them. Yes? It's given by that shift here, basically. So.
And so if I excite harmonically, right, like then it would be linear, right?
So you cannot excite a single atom here anymore. I mean,
yeah, sure, but like if it's a collective state, you're saying it's like harmonic oscillators, then wouldn't be like kind of the shift. I mean, that's kind of if it's harmonic, right, then it's like kind of linear. So like if it isn't this is what I don't understand. So if it's you're saying it's going to
if it would not saturate, that is not, then it would stay there forever. Yes, if there's no saturation, then the shift would always be the same. Yes, the shift just vanishes as the dipole moments here
are getting closer,
are saturating, and they cannot take more photons.
Oh, sure. Okay. Yeah.
And that kills the shift, and that
of course kills the shift. Yeah. All right, and you're saying that happens. I have to think about it more. Like why does it happen at so low densities? That's like
so low photon.
Yeah.